we're going to work with some integrals that have a certain pattern, and the pattern happens to be inverse trig functions. So an inverse trig function, which you should have worked with probably in pre-cal or other things like that, are they're written like this. So an inverse tangent function would be like this, tan -1 of x. Now that does not mean 1 over the tangent of x. Okay, so the negative exponent here does not mean the same thing it does everywhere else. But what it means is, oh, you know, another way you might have seen it is like this, arctan of x. Those two mean the same thing. What it means, it's kind of like going in reverse. When you first learned about trig expressions, you might find the tangent of a certain angle, for instance, the tangent at pi over 4. And so this, the variable x, in this case is pi over 4, stood for the angle, and then your answer would be the tangent at that angle, which was the sine of that angle divided by the cosine of that angle. So since sine and cosine are the same at that location, your tangent there would be 1. Okay, inverse tan is backwards. It like starts with the answer. So inverse tan, this time you would be starting with the actual tangent, and you're trying to find the angle. So you would write it like inverse tan of 1 would be saying what's the angle that gives you a tangent of 1, and so the answer would be pi over 4. So it's what you use if you're trying to find the angle and you already know what the tangent or secant or sine is. So that's what we're doing now, and they have certain integration patterns. They have certain patterns in derivatives, and so there are some formulas you're going to need to memorize for this. You can find them in your book. On page 495, there's a whole chart. We're really only going to concentrate on 3 of them. We're going to concentrate on the pattern of inverse sine, inverse tangent, like I just mentioned, and inverse secant. The others are the same. So like cosine is very similar to sine. It's just negative. Cotangent is the negative of tangent, and cosecant is the negative of secant. So that's why we really only learn those 3. But it goes like this. If you see an integral that has the following pattern, 1 dx, or just dx, over the square root of 1 minus x squared, then that happens to be, the antiderivative of that is sine -1 of x. That's the inverse sine. That's what it's going to look like. So if you took the derivative of the inverse sine, it would look like that. All right. The derivative of inverse tangent would look like this, with 1 dx over 1 plus x squared without a radical. And notice this time we're adding. So I'm writing it as an antiderivative. So that's why I have my little integral symbol. So the integral of dx over 1 plus x squared would be inverse tangent. Again, notice it has no radical, and this time you're adding those two together. And the third one was secant. It's unique in another way because it has that same matching variable out front, and then you have square root, and then this time the variable comes first and the number 1 comes second, and it is subtraction. Okay, you can't vary from that pattern at all. This, for instance, on your secant one and your sine one has to have a negative there. Okay, that you can't be flexible with that. And the tangent has to have a positive. Oh, that's right. Let's finish writing what we have. That's inverse secant. So, your job is just to recognize it when you see it and call it what it is. Of course, you know how it is. It's always, there's a little more to it than that. Sometimes you're going to have to do work to get it looking the way you want it to look. So here might be a sample problem. Oh, let's say we had 5 dx over 9 plus x squared. And I want to find the antiderivative of that. So, first things first, your job is to try to make this look as much like one of those 3 formulas as you can. So, first thing I can do, I have that 5 that I'm just multiplying everybody by, so I can take that out. So I'm going to do that. Again, I can only take it because it's 5 times dx. That's why I cannot take that 9 out, because you're adding. Okay. Next thing, in my formulas, let me drag them back down. So they're over here. Notice that there's always the number 1 in all three of those formulas. In the sine, inverse sine, it's 1 minus x squared. 1 plus x squared for tangent, x squared minus 1 for secant. So I need to make this match, so I need to have a 1 instead of a 9. So what you're going to do is factor out whatever's there instead of a 1. So I'm going to factor out a 9. When you factor something out, you're dividing both things by what you took out. 9 divided by 9 is 1, and I get x squared divided by 9. Okay, so I factored out a 9. Now, because I have 9 times that, now I can take that 9 out, kind of like I did the 5. Whoa, I was trying to move everybody, and we're all in pieces. Up in her. So when I take the 9 out, it is under a fraction bar. It's got to stay under a fraction bar. So I'm getting closer to having it look like our pattern. Okay, what you do now, I'm going to do some u substitution here so that it will look like that pattern. I need just x squared, or just a variable squared here. So what I'm looking for is u squared. If it said 1 plus u squared, that would fit the pattern perfectly. So I'm going to call x squared over 9 u squared, and that's my first little definition. And then you always want to find u by itself, so you're going to take the square root of both of those. That gives you x over 3. And anytime you do u substitution, you always also have to do the derivative of u, which would be 1/3 dx. Okay, and so now let's look at everything we have over here. Remember, when you do u substitution, everything that has an x in it has to get replaced. So I need to know what dx is, and I need to know what this x squared over 9 is. Okay, so dx, well, I have dx right here, so I need to get it by itself so that I know what it equals. So I'm going to multiply both sides by 3. So I have 3 du equals dx, because the 3 and those 1/3 cancel. So in my integral now that I'm rewriting it over here in pink, instead of dx, I'm going to write 3 du. And then I have 1 plus u squared, because I defined x squared over 9 as u squared. Alright, and then, man, that little pesky fellow right there, oh, he won't move. That is funky. Look, he moves separately. That is bizarre, right? Okay. I'm going to scoot that over. Scoot that. That is so weird. Alright, I'm entertaining myself now. That's just not healthy. So, take that 3 out now. So when I take the 3 out, I get 15/9. And I have du over 1 plus u squared. Now, finally, after all that work, I finally have this thing in one of the pattern of one of those equations, which I can't even pull. I mean, there's no way I can pull it back down. Hopefully you wrote it down. If not, they're on page 497. This is in that tangent pattern when I have just 1 in the numerator, 1 and then du, and then 1 plus u squared. It told me that if you have that, the antiderivative of it is inverse tangent of u. Not u squared, but u. Okay. I also have this little 15/9 in front. And so now the last thing you have to do is replace u with what you defined it as. So I've got to go, oh man. Okay. Let's see if I can pull it down. Alright. So up here, here's where I defined u. U is equal to x over 3. So that's what I have to replace right here. So I have x over 3. Now we didn't have any numbers to plug in. There were no boundaries. So this is an indefinite integral, so I need my c. And that's my first example.